Today we're going to talk about so-called optimization. Optimization basically means finding the place where a function is biggest or where the function is smallest. You're interested in maximizing something or minimizing something. Derivatives and extrema, like extreme values. Okay. So one thing that we mentioned before was this thing called the extreme value theorem. This thing called the extreme value theorem. The extreme value theorem says that if f is continuous on a closed interval, then you're guaranteed a place. There exists a place where f of c is greatest. So there's a place where f of c is greatest, and there's also another place and another c prime, let's say, where f is smallest. Now that's not true. So that is, you have some closed interval, say 0, 0, 1, and if you have a continuous function on there, then there's going to be some place where the function is. You're guaranteed a place where the function is biggest. And I think we said suppose so. What if it's on an open interval? What if it's on an open interval? Did we talk about this? I think we talked about this, right? If the function's on an open interval, then you're not guaranteed that, right? For example, even something like the function f of x equals x. Okay. On the closed interval, you see that on the closed interval 0, 1, the function f of x has reaches a maximum value and reaches a minimum value, right? At 1, that's the biggest value. That the value at 1 is bigger than all other values. At 0, the value there is smaller than all other values. But if you're on the open interval 0, 1, then there's no place where you reach a max, and there's no place where you reach a minimum value, right? I think we mentioned this before, right? Claire.
What if you have a straight line in a closed interval?
Yeah, so that's what we mean by that is that's certainly the greatest value, right?
But isn't it also the smallest?
Yes, and that would also be the smallest value.
So C prime and C could be equal.
Could be the same, yeah.
Okay.
So we're not saying that these need not be different points.
Okay.
Yeah. So if the maximum value and the minimum value are the same, then your function is a constant. So this thing basically guarantees you you're on some interval and you have some continuous function, and it guarantees that there's going to be some place where a max is attained and some place where a minimum value is attained. And so what we're going to talk today is how do you find those places, right? And again, we're really talking about a perfect answer, right? Like, how do you find the exact place where that happens? And we don't want to be off even by a billionth, right? Even by a billion, right? Or even, we don't want to be off at all, right? At all. So that's an interesting question. And it turns out that using the derivative is the way to do it. Maybe you can guess, right? Can anyone? Some of you who haven't had calculus before, maybe take a look at this and think, well, where is the maximum value going to occur? Suppose I have something like this. I'm going to draw it like this. Suppose I have something like this. what do you see? Those of you who haven't had calculus before, what do you see about the maximum value? Here's the maximum value, right? Here's the maximum value that occurs here. What do you see happens? What do you see happens at that maximum value with respect to the derivative? Right.
It's like almost zero.
Yeah, it looks like it's zero, right? The maximum value looks like it occurs where the derivative is zero. What about the minimum value? Well, the minimum value occurs here. What about there? What do you see about the derivative? It seems like it's zero, right? So that's going to be the main thing that we'll use the derivative. Maybe it's the case, and in fact it is the case that that where the derivative is zero is exactly the place that you want to look for the maximum value and the minimum value. So, and we'll have to, it looks that way, and we'll bring up some theory we'll make it make sense. Okay, so before we get there, let me put up some language. So we say f has a local maximum at point C if f of C is bigger than or equal to f of x for all x in some interval C minus delta, C plus delta. In some open interval, C minus delta, C plus delta. So local maximum, right? Here you have some function, okay, and this point C here would be a local maximum, right? It's not the greatest value that f spits out, right? It's not the greatest value, but at least locally it is the greatest value, right? So there's some open interval. Here it is. Let's take it. We can find an open interval in which an open interval centered on C, in which that f of C is bigger than all other values. Okay, right? Makes sense. It's like you're locally the greatest. Okay, like within 2 feet, I am the smartest person. Right? I'm the local max wherever I go. Right? Okay. Right? I'm the tallest person, within this 2 foot radius. Okay, so being a local, that's a local maximum. Okay, and of course, also another idea, a similar idea. Say f has a local minimum at C if f of C is less than or equal to f of x for all x in some I'm going to just abbreviate. Whenever I write something like this, n sub delta C, I mean C minus delta C plus delta. This n means neighborhood. The radius delta centered at C.
Really? Is that the neighborhood?
Yeah, that's what we call it, neighborhood. That's a mathematical term, neighborhood. So. Yeah. Okay. So your local max, if you have some neighborhood, if you are the biggest value for everybody in some neighborhood, your local min, same sort of thing. Of course, we say f has a global max C, global max at C, if f of C is bigger than f of x for all C in the domain of f. Right? So the biggest value possible, right? And similarly for global min. Okay. So you have some picture like this. Say, in this picture, the local maxes. Take a look at it. Where are the local maxes? You see them. They're here. Right? They're here. They occur at these heights. Right? So here. These guys are all local maxes, or I guess I should say that these guys are all local maxes, right? With these values, right? And then these things are local mins.
And then the top one is the global max.
Yeah. This one's the global max.
If that's in the boundary, right?
Yeah, that's the endpoint.
Oh, right.
And then this one is the global min down here. Okay, so it's an observation of Fermat. So sometimes this is called Fermat's. In this book, it's called Fermat's theorem. Have we mentioned Fermat before?
Yeah.
Yes.
Yeah.
Yeah. So it's an observation of Fermat, that guy, but a sort of really minor observation in hindsight, but it was brilliant at the time. It's an observation of Fermat that if one f is defined in an open interval around C, and if f is defined in the neighborhood of C, if f is differentiable at C, and f has a local max or min at C. So if all that happens, then f prime of C must be 0. Yeah, Mariah.
Is it like significant that's an open interval around C? Like could
It is. So you can certainly relax that a little bit. So but then you have to talk about. It makes it a little bit more complicated if you do. But yeah, you can. It need not be exactly like that. Yeah. Okay, so so what does this tell you? This tells you that if you're looking for a local max or min, then the places to look are where the derivatives are 0, right? So the consequence of this, let's point. When looking for extrema, one should look where the derivative equals 0. Right. So basically what this says is that what the theorem says is that the only places extrema can occur are where the derivative is 0 2, f is not defined in an open interval around C, or 3, f is not differentiable. Let's see.
So it's two endpoints.
Yeah, for example, yeah, this would be endpoints. Right. Yeah, Claire.
What's an open interval again?
Open interval is something like this, with the endpoints open,
So it,
Like
like the end.
A comma B,
Okay,
A
thanks.
comma B with open intervals, with
So-
open ends.
What's it look like when f isn't defined in an open interval?
So for example, something like this, right? So here's an example. Look, somebody might say, well, you said Fermat's theorem says that the derivative is going to be 0. Here's an example where the derivative is not 0, right? The derivative is not, it doesn't look like the derivative is 0 here. And my answer would be, well, f is not defined in an open interval around that point, so that's okay, right? We said in places where extrema, what Fermat's theorem says is that extrema are going to occur at these three places. Either the derivatives exist and it doesn't 0, and it's either the derivative exists and it equals 0, or the derivative doesn't exist, or the function isn't defined in an open interval. Okay, so these are the three possible places three kinds of places that the function can get a max. And say, so that's category 2, right? And then somebody would come along and say, well, what about this? Here's a max, and the derivative isn't 0, and the function is defined in an open interval around it. My answer would be, well, f is not differentiable at C, so this falls into category 3. Okay, so these are the only 3 kinds of things that can happen, right? Either your function is differentiable out there and the derivative is 0, or you're at an endpoint, or you're at some place where the derivative doesn't exist. Okay, so this is what Fermat's theorem tells you, that those are the only kinds of places where extrema will occur. Yeah, Mariah.
So around C it has to be an open interval, but then the whole function has to be on a closed interval. Is that correct?
That's right.
Okay.
That's right. Yeah. Well. The whole function has to be on a closed interval to apply the extreme value theorem.
Mm-hmm.
Okay, but that's for Fermat's theorem. That's separate from the extreme value theorem. Okay, this is just talking about in general. Whenever you have any sort of function, right? Whenever you have any sort of function, and it could be on the whole line, say, right? Keep on going. Okay, it could be on the whole line.
Okay, so it doesn't have to be confined.
Right. This is just a general theorem. Now you have this other theorem saying that if you are on a closed interval and you're continuous on the whole thing, then you're guaranteed a max and a min.
Gotcha.
So that's a separate statement. Yeah. Good. Other questions? Is this making sense, Stefano? Yeah.
Maybe several at the same time, like 1 and 2.
Yeah, could be, right? Yeah,
For local or?
yeah. So, for example, for us, when we define the derivative, we actually assumed that it had to be defined in an open interval already. So, for us, basically, there is no derivative here. Yeah, but yeah. So, other questions? Okay, so anyway, the moral is that you have this thing called Fermat's theorem, and it tells you where maxima and minima could occur. Okay. So let me. So let's just briefly say why Fermat's theorem makes sense. Why is Fermat's theorem true? Okay. Why are you guaranteed that the derivative is going to be 0 there, right? y must f prime of c equals 0. So you can sort of think of this in a picture. Okay. You have some function. You have some function, and you know that this thing is a max. Okay. So let's say that f has a max at c, has a local max at c. Okay. So all we know is that it's bigger than everybody else nearby. So it's bigger than everybody else nearby. Okay. Now let's think about the derivative. F prime of c. We're trying to see that the derivative is 0. Well, let's look at the derivative. How do we define the derivative? Anyone remember the definition of the derivative? Yeah, Victor.
Slope of a tangent line.
Slope of the tangent line. Can you give me the limit thing?
Oh, the limit of b minus, wait, f of b minus f of a over b minus a.
Well, so we're taking a c, so let's remember. Wait.
Of f of x plus c plus h.
C plus h.
Plus f
Right, so f of c plus h minus f of c over h, right? In this thing, okay. So let's suppose that that we're going from the right hand side. Let's suppose that h is some positive number. So we're taking c plus h. Okay. Well, f of c is the biggest thing nearby. And we're looking at f of c plus h minus f of c. What can you tell me about that? Don't believe it. But did everyone hear that? Good. If you didn't hear it, good. What can you tell me about f of c plus h minus f of c? If f of c is the biggest thing nearby, f of c plus h is smaller, and so you're taking something smaller minus something bigger, and you get a negative number, right? And then you're dividing by a positive number, right? So you've got a negative number over a positive number, so you know that this thing, whatever it is, it's a negative number. Right? What am I going to say next?
You're coming from the other direction. That's going to be
Good. I was going to say don't blurt it out either, but you don't talk much anyway, so it's good. Yeah. So take it from the other side, and then you see that what you finished it up, right? You see that it has to be it has to be a positive number, right? So this number, take it from the other side, it has to be a positive number, or at least a non-negative number, right? It has to be a non-positive number. It also has to be a non-negative number, right? In other words, it must be 0. So it must be 0.
Is that going to be our bonus on the next test?
What?
Is that going to be our bonus on the next test?
No. No. But I might give Sarah a bonus. I think I'll give Sarah one bonus. Yeah. Okay, right. So you see it. Why is the derivative 0? Well, if you're a local max, then the derivative, you see what happens. The derivative has to be non-positive, and it also has to be non-negative. So take from the other side, consider the limit as h goes to 0 from the negative sign. You see that the derivative also has to be greater than or equal to 0. Who's raising their hand?
I had a question. So is it less, or it's greater than 0, or
Greater than or equal to 0.
greater or equal to 0 if h goes to on the left side of 0 because h is negative?
Yeah, h will be negative, but you'll have a
that
negative
would be
number. You'll have you'll have so you'll have the limit of f of c plus h minus f of c h as h goes 0 from the negative side. So again, you have something smaller minus something bigger.
Right, so
That's
that
what's
continues
negative.
negative.
That's still negative, but the bottom is now negative.
Okay.
So now it's greater than that. Okay. And so that's the proof of Fermat's theorem, right? That if your function is differentiable at a point and has a local max there, then the derivative has to be 0 there. Okay. And that theorem gives us gives us basically a method of finding local maxes and mins, right? It says that basically gives us to look for the only places they can occur are these 3 points, these 3 sorts of places, and so it's easy to find them. So let me do an example. Okay, so let's do say f of x is say x minus 2 squared plus 3 on the interval 1 over 3. Well, no, actually, let me just do it like this without the interval. So on the whole line. Okay. So what do? We say, well, we need to find places. We need to find these 3 sorts of places, right? Now, this function is differentiable everywhere, right? This function is differentiable everywhere, so and it's defined on the whole line. So 2 and 3 don't exist, right? There's nothing that falls into these 2 categories, right? So the only thing we need to do is find out where f prime equals 0. Right? So what's f prime? Right? So, and where is that equal to 0? Well, f prime equals 0 when x equals 2.
Extrema doesn't have to satisfy all 3 of those, it only has to satisfy 1.
An extrema will occur. These are the only sorts of places where extrema will occur.
So, but you just need to fulfill 1, you don't have to fulfill all of them.
It's impossible to fulfill all of them, right? Because you can't be like the derivative is 0 and the function is not differentiable there, right? That wouldn't make any sense. So you look for where extrema occur. Either this happens, or this happens, or this happens. Okay. So, right. So that's so x equals 2 is a possible extrema. Right. And in fact, you know what it is. You know that it is, right? Right? Because of your knowledge of parabola. Right? This is just a parabola shifted over, translated over. Okay. So in fact, and so Fermat's theorem does actually pick off the right point. Yeah.
Why is it a possible extreme?
Well, you don't know if it is or not. You just know that it's possibly.
But isn't that what the theorem said?
No. It just says that the only places they can occur are these places. It's not saying that if this happens, then it is an extrema.
That doesn't seem very useful.
But it's more useful than not having any information.
I guess.
Yes, Stefan.
So could you say it's 100% sure that that point has a local extrema, but not, no?
No.
I'm not sure. But
Yes.
it doesn't dictate, I mean, other than if you look at the graph, whether or not it's a maximum or minimum.
No, actually you don't know that either.
What is
there a way to
this?
verify?
Okay, hold on. Okay, let's do another problem. Okay. You see, the thing is that the thing is that no. Let's do the second one. So example 2. Maybe this will pacify to some degree. F of x equals x minus 2 plus 3 on 1, 4. Okay. So now 1, 4 now that we're on 1, 4, we know that there's going to be an absolute max and there's going to be an absolute min. There's going to be a global max and global min. So we're guaranteed a max, a global max, and a global min. Okay. So I mean, in this case, we know it. We knew it because we knew about the parabola. Okay, but if it weren't a parabola, we wouldn't be so sure. Okay, we wouldn't be so sure. But here we have some function on a closed interval, closed and bounded interval, and so we know there's going to be a global max and there's going to be a global min. Okay. So we do the same thing again. We say, okay, where is f prime equal to 0? Well, that happens at x equals 2. Right? And in the second group, where is f not defined on an open interval? Well, that's at 1 and 4. Right. Right. And where's the function not differentiable? Well, you could also think of that as at the endpoints it doesn't have a derivative, but everywhere else it has a derivative. Yeah, so category 3 is sort of subsumed by category 2 for us. Although one can actually define like half-sided intervals, half-sided derivatives, excuse me. Yeah. Okay. In any case, so what does this tell us? These are the possible places for extrema, right? So possible locations. It's not just that they're possible, they're the only possible, right? The only places extrema occur are 1, 2, and 4. Right? Yeah, I should make that clear. It's not just that it's possible. That's the only possible place. Okay. These are the only possible places. And so you say, okay, well, further, we're guaranteed a global max and we're guaranteed a global min. So all we have to do is check these 3 places and see which one is the biggest, and that will be the global max. And check which one is the smallest, and that will be the global min. So you just plug it in and say, okay, f of 1 is 4, right? F of 2 is 3, and f of 4 is 7. Right? So this one is the min, is the global min. This one is the global max.
And in order to find out if the f at 1 is 4 is a global max or min, can you check the limit as it approaches both sides?
The limit is just going to be that value.
But I'm saying or I guess the derivative or the slope, like as it approaches that point, like if it's negative on the left and positive on the right,
Yeah.
then it's a min.
Yeah. That's the way to do it. Yeah. Have you seen that before, Stefan?
Yeah, I was just remembering now.
I was going to give you a bonus point, but
No,
forget
I
it.
don't.
Yeah, good. Yes. So and if you check the picture, right, 1, 2, you see what happens. Right, the graph looks like this, something like this. Right, the global min is here, the global max is here. Right, at 2 and 4.
What was Stefan saying? About 4? What was Stefan saying? About 4? Stefan, what was
he was saying that if you suppose you're looking at this thing here, and you look at the slope of the tangent line, you look at the derivative on the right-hand side. Well, the right-handed derivative is negative, right? So you know that this thing is a max, is a local max, right? Because the function values are dropping. Okay. Yeah, so I didn't have this example in, but maybe I should put it in. F of x equals x cubed on R. Okay. So what should we do? Let's check the place where f prime is 0. Right? F prime is 3x squared. Where is that equal to 0?
0.
At 0, right? Okay, so that is the only possible place that you have a local maximum. Okay, but in fact, is there a local maximum there? No, right? Because you know what the cube function looks like. Right? There's nothing there. Right? It's not at that point, you know, we got our hopes up because Fermat's theorem says that that's a possible, and in fact the only possible place for a local maximum. But in fact there's nothing there at all. And later we'll see, we'll make more tests that will allow us to tell without graphing what if there is a maximum there. Yeah. So okay. So let you do a couple of exercises. One is say cosine on the real line. So maybe take 1 minute and do that. And I'll pass back papers while you're doing it.
Oh, yeah. I think 0 and also yeah.
Okay, turn somebody nearby and talk with them. Okay, so what's the answer? Where are the only places that extreme values can occur? Madeline?
So it's not like whenever x is an interval of, or a value of pi, so like 0, pi, 2 pi. Yeah, so I wrote it as x equals k pi.
So x equals k pi here. So right, f prime of course is sine, right? And so you're wondering where the sine
It's negative.
I'm sorry, negative sign. So where is sign equal to 0? Well, it's equal to 0 at any integer multiple of pi is how we say it. So at any k times pi, where k is an integer.
Does that include 0?
Mhm.
Okay.
The integers 0, 1, negative 1, 2, negative 2, etc. Okay. And you see that that's true, right? If this is the cosine, then you know it actually has maxes and mins at the integral multiples of pi. Another one. F of x is x e to the x. Yeah, Claire.
I just have a question on
Yes.
this one.
Yes.
So if you had like a range from 0 to 2 pi,
Yeah.
would there be a maximum, a global max? Because wouldn't there be 2 points that are the same?
Yeah, both of those would be considered global maxes.
Okay.
Yeah,
Okay.
it need not. There's nothing that says that there can only be one global max.
Okay.
Like constant function, all values are global maxes and global mins.
Okay, cool. Thank you.
Okay, turn to somebody next to you and talk, please.
So it's
Because it's a product. So it's yes, okay, wow.
Okay, so what's the end? What do we get? F prime is what? F prime is what?
U to the x
X.
plus x dx.
Okay. Right. The derivative of the first guy, 1 times the second, plus the first guy times the derivative of the second. Right. So is that equal to 0 anywhere? At negative 1, right? So this is 1 plus x e to the x. Right. You factor out, you distribute out the e to the x, right? You see that this can be is 0 when x equals negative 1. Right. The only thing that could happen is, you know, either this is 0 or this is 0. E to the x is never 0. The only way that this product could be 0 is if 1 plus x is equal to 0. Right. E to the x is never 0. It's always a positive number.
So there's possibly a minimum.
There's possibly a minimum there, but you don't know. Right. Okay, so right as you see that there's something, you know, still more work needs to be done to make this a bit more complete, and you know, you'd like to have some surefire way of saying and that's going to be a max, or that's going to be a minus, things like that. And we'll develop some partial answers to that. Next class, we'll be talking about some pretty important theorems, Rolle's theorem and the mean value theorem. So I suggest taking a look at the material before.